So in this video, we'll continue our discussion on the integration of rational functions. Please look at the page here and please recall the fact that the degree DEG means the highest power of the polynomial. And in the case of irrational functions, in the case A, we're talking about the degree of the denominator is higher than the degree of the numerator. And in the last two videos, we have talked about two cases already, which are the first two cases here. So in the case A, where the denominator has a high degree, you need to completely factorize the polynomial first. So I'm talking about the factorization of the denominator. And in the case where all the factors are different and all of them have degree 1, and that was the video we talked about in part 1. And in the category 2 case, which is the part 2 video, we talk about the case where all the factors are different and some factors may have degree 2. So these two cases, we have talked about that already. And in the current video, we'll talk about the next case, which is the case where some factors are repeated in the factorization of the denominator. So let's look at the case together. As you can see, the degree of the top is 2. Denominator, the degree is 3, right? So we can continue our discussion. And now, I actually gave you the factorization of the denominator already. You actually have 3 factors. All of them have degree 1. And please check the fact that these two factors are actually the same, right? And let's see how to do the partial fraction decompositions. So let me write down what you have inside the rational fractions. And by the partial fraction method, because now you actually have 3 factors. So we understand that there should be 3 smaller pieces of fractions on the right-hand side. And it really depends on the factors that you have. Now you have 3 factors. And please recall the fact that when the denominator has degree 1, we need to use a constant at the top, ABC like this. Now it makes quite a bit of sense in the sense that you actually have degree 3 in the bottom and we need to solve for 3 constants. So in general, the degree of the denominator needs to be the same as the number of constants you have on the right-hand side of the partial fraction decompositions. So anyway, the only thing that does not make sense yet is the fact that these two fractions are the same. We don't want them to be the same. In the partial fraction decomposition method, no pieces of the fractions should be identical. And because of the fact that x minus 2 is a repeated factor, and the fact is we have to increase the power of the second piece by 1, which means it actually has the power 2 in the denominator. So please think about how to solve for the ABC later. But for now, just to give you more examples. For example, please look at the red color. In the case where now you have actually 4 degree 1 factors in the bottom. And the fact is that x plus 2 is repeated 3 times. What you need to do is you actually now need 4 pieces of fractions because of the fact that you actually have 4 factors, right? So let me write down all the 4 factors first. And because all factors are degree 1, so what you are doing is we need to add the constant ABCD at the top. And because the x plus 2 is repeated 3 times, so what you need to do is to think about the 3 identical fractions now. We have to keep increasing the power of the repeated factor 1 by 1, starting from the second fraction. And that's the way to write the partial fraction down if you have the repeated factor. And anyway, let's come back to the purple case. Try to get ABC first, and after that, we have to do the integrations. So now, please think about the top in the right-hand side. The fact is now I try to make the denominator the same on both left and the right-hand side, right? So in the case, we can actually compare what you have on the numerator. But let's think about, for example, the first term. The first term actually comes with the factor x minus 2 itself. So when you expand it to a bigger denominator, the fact is that you need to just multiply to 1 copy of x minus 2 to get to x minus 2 squared and 1 copy of x minus 3, right? And similarly for the second term b, because b itself actually comes with 2 copy x minus 2 already. You just need to multiply to x minus 3. And similarly for the last term c. C itself is in the partial fraction which has the x minus 3 in the denominator, so you need to multiply to the factors it doesn't have. So I think C needs to multiply to only 2 copies of x minus 2. And you see now that's the completion of the right hand side. And because now the denominators are the same on both ends, we can just compare what you have on the numerator. So please look at what you have here, and you need to find ABC, and you have to try to use some clever choices of x to resolve this problem. And I believe that we have to check out the roots of the factors you have on the right hand side. For example, if you choose x equals 2, it is a good choice in the sense that the last term would be 0, right, when x is 2, and also the first term would be 0 when x is 2. So let me replace x by 2 on both ends. So now we have only the middle term, which is b, and I believe that we can find the b now. The fact is that if you do the arithmetics, we'll get that minus b actually equals minus 3, which means that b is actually 3. And we can find also the other constants. Let's say I can choose x equals 3. It is a good choice because when x is 3, you see the first term is 0 and the second term is 0, which means we can find c from here. So if you do the arithmetics, you would see that c is actually 1. And for the remaining constant, it doesn't look like we have another good choice of x to choose from, because if you look at the right hand side, only the choice 2 and 3 are the roots of the factors available on the right hand side, right? And but anyway, now the good thing is that we have C already. Finding A is actually clear for any choice of x, because we can just replace the value of B and C in to find A. For example, I can just choose any random value now. Let's say x is 0. When I choose x is 0, the left hand side is 7. And the right hand side would be a times x0 minus 2 times 0 minus 3, and b is itself 3. It is b. We found it here. So 0 minus 3 for the term inside the bracket, and is 1. And the last factor is 0 minus 2, the whole thing square, right? So let's do the arithmetics together. So if you do the arithmetics, you would get that 6a is actually the same as 12, and which means that a is actually 2. Now please check the fact. We actually obtained all the constants ABC already. Let's come back to the integration problems. So please look at the calculation now on the right hand side for the integration problem. The first term is actually easy because it's a degree 1 factor in the denominator. So we can use the ln function. 2 is the constant for the A, and 3 is the constant for the B, and 1 is constant for C, right? And 2 times ln of x minus 2 is the answer for the antiderivative of 1 over x minus 2, right? And similarly, for the last term, it's also clear. It should be 1 times ln of x minus 3. How about the middle term? It's 3, which is the constant at the top, times something. And please check the fact that now the bottom doesn't look very easy, because you are asked to integrate 1 over x minus 2, the whole thing square, right? And but this case is actually easier than the case like the degree 2 factor we saw in the last video, because we can simply use the power rule. Now we can take it in the form that we can write it as the exponent minus 2 instead of looking at it through fractions. And by the power rule, we understand the answer is just like this. So it means that inside the bracket, the answer is minus 1 over x minus 2. And that's the answer to the whole problem here.